Hi, this is an example problem on time dilation from special relativity in chapter 28. Pause for a moment to read the question. So in this case, we have a spaceship that's flying. It's flying past Mars, and we're given some information. There's a signal light that flashes on and then off, and it takes a certain amount of time. According to an observer on Mars, the spaceship flies overhead 1,200 kilometers. Part A, we're just asked a question to explain. Consider the pilot of the spacecraft and the observer on Mars. Which person measures the proper time interval between the events light turns on and light turns off? Explain. And part B, we're asked, what is the duration of the light pulse measured by the pilot of the spaceship? So in this case, we're looking at measurements of time made by two different people or two different observers, and these are in different frames of reference, which is to say they are moving at constant speed with respect to one another. Now, each of the observers in their own reference frame believes themselves to be at rest while the other person is moving. Because of this, the two observers will measure different time intervals between the same two events. Now, we have an equation for time dilation, which we can use to solve this type of problem. You can see here we've got delta t equals gamma delta t0. Now the book doesn't use gamma, they just use this expression, but I like to use gamma in the equation and then solve this using this expression, which involves a speed v and c. You can always plug this right in here anytime that you need, but this simplifies the way the equation looks a little bit. Now the important thing here is this gamma factor here that I've written. It is a factor that relates the time measured by one of the observers. So delta t0 is one of the time measurements. Delta t is the time measurement made by another observer. And the gamma, it's always greater than or equal to 1. It's only 1 if the two observers are in the same reference frame. If they're moving with respect to one another, it's greater than 1. So we can see that delta t is always going to be bigger than delta t0. Delta t0 is what we call the proper time interval. It's the shortest time. And so the important thing when we're doing time dilation is to identify of these two observers, which one measures the proper time, which one measures the longer time, which we call the dilated time. So let's copy this time dilation equation. And then in part A, we're going to figure out which of the two observers, the Martian based at Mars or the space traveler, is observing the proper time. So I've posted in the relevant equation for time dilation, and we're going to identify in part A who measures the proper time interval. Is it the person stationary on Mars, or is it the pilot of the spacecraft? Now let's look at the definition here for proper time interval, because this is really important. It says the proper time is measured in the unique, which means the single reference frame, where both events occur at the same location in space. Now, an event in special relativity is just a space and time coordinate. And two events mean that you have two separate things that have occurred in space and time. In this case, it is the flashing on and then off of the light. Let's draw this picture for the observer on Mars. So let's say here's the surface of Mars. Here's a little tower here maybe that has the light bulb on it. And this light can flash on and off. So let's see where this event takes place according to the observer on Mars. So here's the observer on Mars, kind of just standing here. And they can watch it. And I'm going to mark, say along the x-axis, perhaps, what's the spatial coordinate when this thing turns on? Well, for the Mars person, they're standing there at rest with the light, and when it flashes on, it occurs at some position on the x-axis that, let's say, I'm going to call it x on. That's the position. Of course, you could say y and z as well, but we're only going to consider the x-axis for this purpose. Now, that's the position where it turns on. Now, we wait for some time, and a second event is that light flashes back off. Where does it happen according to the Mars observer? Well, it happens in the exact same spot, because that spot's not moving with respect to that person. The light's not moving, and so it turns off and on at the same spot. That is to say, both events occur at the same location according to the Mars observer. So it is the Mars observer who, in part A, is going to measure the so-called proper time. Proper time doesn't mean that there's anything special or proper about it. It just means that it's observed, the two events have observed occur at the same location in space by that particular observer. So I've gone ahead and written this up for part A. Proper time delta T0 measured by the Mars observer, since the two events, lights on and light off, occur at the same position in their coordinate system. According to them, it's the same location on their x-axis, which means that for part B, what is the duration of the light pulse measured by the pilot of the spaceship? Well, that's going to have to be the dilated one. Let's look at part B here. So before I go ahead and calculate the value for part B, just want to show you what the spacecraft observer is seeing here. So here's your spacecraft, right? And there's some person in there. And what do they see? Well, initially they've got the light over here, right? And when it turns on, we could say that this is the position. Actually, they're 1,200 feet above, right? So something like 1,200 meters, I'd say. Does that matter at all? It doesn't matter because the direction of motion in this case is along the x-axis. And so vertical distances don't matter. This 1,200 here, this doesn't matter at all. Okay, kilometers is what it was. Now, for this space shuttle observer, this is the spot we can say for them. I'm going to call it X prime for their coordinate system. This is on. But what happens is the light stays on. This whole thing here is traveling towards the space shuttle because the space shuttle thinks it's at rest. So we've got, you know, this light moving with some velocity in that direction. And once the light finally turns off, according to the space shuttle, who thinks they're just sitting there at rest from their point of view, watches this light has moved this much closer to them. The two positions, X on and X off prime, these guys are not the same. Therefore, this is occurring at two different spots. This is a dilated time. Now, to calculate that dilated time is pretty simple. We just got to go ahead and use the equation there. So delta T, move this over a little bit. Delta T is equal to gamma times the proper time interval. Now, we know that the proper time interval is measured by the Mars observer, and that is equal to, according to this, 82.4 microseconds. We also know the speed here, 0.978 c. We can use this formula to calculate the gamma factor. So let's do that. So we know here delta T naught is equal to 82.4 seconds. And now to calculate the gamma factor, that's 1 divided by square root of 1 minus v over c squared. And usually, a lot of times, they'll give you the speed as a fraction of the speed of light, which they've done here. It says it is 0.978 c, which is nice because now we can say 0.978 c divided by c, whole quantity squared. These guys cancel. And when we put that into the calculator, we get 4.79. So that's our relative to gamma factor. And now we can figure out what the dilated or longer stretched out time is. It's going to be gamma delta T0, which is 4.79 times 82.4 microseconds. There was a micro in there, I recall. which comes out to 395 microseconds, and that is time interval measured by the pilot of the spacecraft. And let me just clarify that since the positions being different means that it's dilated time, I'm going to just add this here to the special case here. This was the proper time because the spatial positions are the same for the two events, on and off. Same position in the coordinate system of the Mars observer only.